Hello, I'm Eva Guachon from the University of Picardie Jules Verne in France and the IST CNRS in Japan. I'm going to present the work done by my colleagues and me on camera model conversions accepted to appear in ICRA 2024 proceedings. There is a wide variety of camera projection models, some of which are mentioned here. We may find ourselves working on several different datasets. For example, our DC image dataset created with the Azure Kinect camera uses the rational polynomial distortion model, while the Panoramis dataset uses a unified central model with a catadioptric camera. To make software work with these datasets, it's necessary for the model to match. Currently, Stella Veslam, a vision-based simultaneous localization and mapping algorithm, uses a Brown-Conradi projection model. The only current way to use the algorithm with our datasets is to calibrate the camera in the algorithm's model, which is time-consuming and doesn't guarantee the availability of the calibration images or the camera itself. Our method circumvents this issue by converting the models without using calibration images. To convert the different models, we start from the pinhole model to obtain a distortion-free digital image. Then we integrate the tangential and radial distortions depending on the specified model with the D parameter. This yields UD and VD, the coordinate of the pixels of the digital image with distortion. Let's consider the example of the Azure Kinect camera in the rational polynomial model, which we convert to a Brown-Conradi model to use Stella Veslam afterward. We solve the following equation. Then we can directly identify the parameters alpha u and v, u0, v0, p1, and p2. Next, we solve the linear equation with virtual points in the image. We obtain the different camera parameters on the converted line. The calibrated line corresponds to the parameters obtained with calibration via mixed vision, allowing us to compare our converted parameters. The factory line lists the camera's factory parameters and represents a naive approach to model change to demonstrate the importance of converting parameters. For factory parameters in rational polynomial model format, we remove parameters k that do not match between the two models. We use P1 and P2 for the factory 6P trajectory only. For this example of the narrow field of view trajectory by height 15 Hz, we observe that the trajectory obtained by Stella Veslam with the converted parameters is much closer to ground truth. This ground truth is obtained by a motion capture system. The table lists the relative and absolutes cause errors of rotation and translation. We notice that errors with the naive approach are much larger than the other two in translation. Moreover, error values with converted parameters and calibrated parameters are close, demonstrating that our method yields similar results to calibration without needing to calibrate the camera. In our article, we highlight other results and conversions, such as the transition from the equidistant model to the unified central model, and from the unified central model to the polynomial Cartesian model. Regarding the rational polynomial model to Brown-Conradi model conversion, we analyze 6 other trajectories from our dataset and their pose errors. Altogether, this demonstrates the effectiveness and importance of our conversion method. Currently, we are working on other camera model conversion. Thank you for your attention.